Namaste everyone, welcome to wave optics class. Somehow we were struggling to understand what is path difference, what is phase difference. At the end we were able to understand to a little extent what is actually path difference, what is actually phase difference, and what is the what are the conditions for production of a very strong wave, that means the constructive interference, and what is the condition for destructive interference. All these things we have seen. So we will go to Young's double slit experiment and we will find out how the waves will interfere and how the pattern is produced on the screen. If you place or if you allow the two waves to superpose on a screen, how the types of patterns are produced. Now Thomas Young did the experiment by taking a cardboard and making very fine holes inside it, and of course it is not a simple cardboard, and in front of this there is one more slit, very fine slit, and a source of light is kept in front of this first hole. So this is slit S1 here, and here is a source of light. A source of light is kept in front of a single slit, and in front of the single slit there are two slits, very fine holes, and light from this and moves like this and it passes through these holes, and then they start interfering here. They start interfering, and these two sources of light are actually derived from the same parent source. So if you just examine those two sources of light, then you will definitely find that the two sources of light have the same wavelength, and they have same frequency, and they have same amplitude, they have equal amplitude. If the sizes of the slits are very equal, then they are called coherent sources. So we must be acquainted with a few terms here. One is coherent source. So what do you mean by coherent source of light? Sources of light which have constant phase difference, and if they are separated they should have a constant path difference and phase difference, but they should have equal wavelength and nearly equal amplitude. Why do we take nearly equal amplitude? And you know, if two waves superpose constructively, and if the crest falls on crest, the amplitude will add up. It will be A plus B. Say 4 centimeter plus 3 centimeter, 7 centimeter. The new wave will have an amplitude of 7 centimeters. It's a beautiful wave now. If they fall with crest on trough, 180 degree out of phase, right? One crest falls on another trough, then the amplitude will decrease, 4 minus 3. And the resultant wave will be a smaller wave. Suppose you want to have the resultant wave completely vanished. What you need actually, you are in need of two waves which are having same amplitude. If the amplitudes are same, when they add up, of course no problem, intensity of the resultant wave will be highest, A plus A, 2A, but when they fall with the crest on trough, they vanish completely, A minus A, 0. So if in that previous problems when you are superposing the two sound waves, if you don't want to hear any sound at a place, then the amplitude of the two waves should be equal. Otherwise what happens is, if the compression falls on rarefaction, and if the compression and rarefaction amplitude of the two waves are not equal, for example, amplitude of one wave, sound wave is say 6 centimeter, amplitude of another wave is say 3 centimeters. Then 6 plus 3 gives 9, okay, it is a strong wave. 6 minus 3, it doesn't give 0. So the places where you get minimum sound will not be the zero intensity sound places. If you want to get zero intensity sound, then the amplitudes of the two waves must be nearly equal or almost same. Then you get, so in terms of light you think of, when the two light waves superpose, if the crest falls on crest of the two waves, then you will get bright position. And if the crest falls on trough, if the two waves vanish, you will get dark position. Suppose the amplitudes are not equal, think of the situation. The places where the crest fall on crest will be bright. But when the crest falls on trough, if the amplitudes are not the same, 6 minus 3, then there will be something remaining there. Then dark places will not be perfectly dark. So coherent sources are the types of sources which have a constant phase difference. That means if the one wave is lagging behind another wave by 3 lambda, every time, everywhere it is 3 lambda, right? They have a constant phase difference, constant path difference, and they have almost equal amplitude or nearly equal amplitude, such sources are called coherent sources. Definition wise, examination wise important, and understanding wise is also important. So you should have coherent sources. Sir, where do we get coherent sources? Can we purchase 2 bulbs from the shop and say that they are coherent sources? Sir, we have purchased 2 bulbs from the same shop and we have paid same price and they are from the same company, it's identical to C, they may not be coherent. The light emitted from 2 different sources, 2 different tungsten filaments, may not be of same wavelength. There may be a small difference. They are not coherent. So if you want to get coherent sources, divide the single source into 2 sources. You split it into 2 sources, then that acts like coherent sources. So these 2 act like coherent sources of light and they interfere and they produce interference pattern. Now we will analyze it. Okay? We will analyze the Young's double slit experiment. Okay? So I have 2 sources. I will show only 2 sources of light. And before that I have 1 source and all those things I know it. So I will take 2 sources. I will name it as S1 and S2. Let the distance between them be D. I'll take H dash D. And remember always in the previous class, in the PPT class, I was discussing about one point. When the waves superpose, when the 2 waves superpose, they should not meet at larger angles. That is a problem. Suppose one wave, light wave, meets the crest of another light wave like this. You see, the displacement of this is like this, displacement of this is like this. How can they add unless they are in the same direction? So if the amplitude of one wave is like this, amplitude of another wave, or displacement of one wave is like this, or another is like this, they don't add up. And for the superposition to happen clearly, the angle at which the 2 waves go must be very small. They must be almost parallel to each other like this. If they have to be parallel to each other, the screen what we place must be at a very large distance compared to the distance between the 2 sources. The 2 sources must be separated by a very small distance and the screen must be at a very large distance so that when the waves go and meet each other, the crest exactly meets the crest. They will not be at some other angles like this. They should be at the same direction. So for that one, the angle of interference, the angle which they meet should be very small, right? Otherwise, if they meet one like this, another coming like this, then the amplitude, the displacement of this is like this, displacement of this is like this. That is not an interference. Okay? So for that, D must be small. Okay, I'll write it here. D very small compared to D, or simply I can write like this: D, capital D, much greater than D. The distance between the screen and the sources is capital D, which is large, and distance between the sources S1 and S2 is very small. Now you start applying the theory. Where will you get bright spot? Where you will get dark places, and we call them as fringes. The places where the light interfere constructively, they are called maximas, the bright places. The places where light interfere destructively, they are called minimas, dark places. Definitely this perpendicular bisector here should be a bright fringe. You agree that now today, right? Because you know all those things. A wave starting from here, it was keeping its wave positions like this. The wave starting from here will travel equally and the crest of this falls on the crest of this. They must interfere constructively. This should be a bright fringe. I will write it as B0. It is the 0th bright fringe. First bright fringe. It must be a bright fringe. Whatever the color of light that you use, this must be a bright fringe. Whomever be the person starting from here and here, whether the 2 persons are having 1 feet foot length or half feet foot length, whatever it is, foot length doesn't matter, it should be same. They will meet with the identical conditions here. Phase will be same by the time they meet here. It should be a bright fringe. Now let us take a point on the screen here, such that this wave travels a little bit more and this wave travels a little bit less. How much less? Lambda less. Say this one is 5 lambda, and this one is 4 lambda, 1 lambda less. Then the fourth crest of this falls on the fifth crest of this, again bright, first bright fringe. So path difference of 1 lambda, right? No path difference, just recalling the previous discussions. What about in between here? The wave traveling from here to here, right? Wave traveling from here to here, and wave traveling from here to here, they have a path difference. This travels more, this travels less. How much less? Say 0.5 lambda. This travels say some 4.5 lambda. This travels or this travels 4.75 lambda. This one say, okay, this is 3.5 lambda, this is 4 lambda. Then the difference is half lambda. So path difference is half lambda. This is dark fringe, first dark. There is no zeroth dark. Here you don't get dark fringe at all. You get dark fringe here. So there is the dark fringe numbering starts from 1. Bright fringe, bright place numbering starts from 0, because we have a first bright place here which is unique. Whereas then you will get dark, bright, dark, bright. So what do you mean by fringes? This is the pattern what you get. So if you take a photograph of this screen, that appears like this. At the center place you will have brightest place. And as you move away, the brightness goes on decreasing. It becomes dark. Again it becomes bright, dark, like this. So here it becomes dark, again bright. So you will get bright, bright, dark. Below also you will get another bright, right, and another dark here. So bright, dark, like this. So you will have a pattern which consists of, at some places very bright light, at some places dark light, at some places bright light. And if you draw a graph of intensity versus distance, here the maximum intensity, of course we will write the formula for intensity later. We will derive an expression for fringe width today. What are fringes? These are all fringes. So they appear like this. They are called fringes. The distance between two successive fringes is called fringe width. The two successive bright fringes. Sir, what about two successive dark fringes? Distance between two successive dark fringes is also fringe width, because all the dark fringes are equally spaced. Say for example, the distance between two dark fringes is 2 millimeter. This distance is also 2 millimeter. So distance between two successive bright fringes or two successive dark fringes is called fringe width. And if you see that the dark fringes are dark and intensity is 0 almost, bright fringes are very bright where intensity is highest. And if you draw a graph of intensity versus distance, you will find that intensity here is maximum. So here is intensity. I have rotated the graph, and here is the distance, x, like this. I have rotated the graph. So intensity here is maximum. By the time you reach here, intensity is 0, because intensity is along this axis. By the time you reach here, again intensity maximum. The brightness of this and brightness of this are same, because they are the places where amplitudes add up. A plus B, A plus B, A plus B everywhere. Intensity here is maximum. So a graph of intensity versus distance will be like this. This is the central bright fringe, and this is the first bright fringe on one side, first bright fringe on another side. This is the dark fringe, this is the dark fringe. Bright fringe 0 comes to only bright fringe at the central fringe. Now distance between these bright fringes, successive bright fringes, is called fringe width beta. We call it as beta. The distance between two successive dark fringes is also called beta. Now today our job is to find out the value for beta. That is my job. So I don't rub now onwards. I will simply keep on writing on the board. So if you have a pen and paper, take it out and start writing. Without pen and paper, now the next derivation has nothing to do. So you must take a pen and paper and you have to start writing the things. Okay? Okay, first two sources of light. S1, S2. And they should be very close, but I can't show very close in the diagram because I must get marks in the examination. If I write very close and draw the two waves interfering, going parallelly and interfering at very small angles, I won't get marked because I want to identify everything here. So this is, okay, I'll write D later. I write D later. S1 and S2, and here is a single source that is not needed for us now. So this is the opposite point here, and here is a screen which is at a distance of capital D, which is much away. So this is so keep on writing this. Take a paper and write this. Don't look into the video as it is. Be ready with pen and paper. And this is the perpendicular bisector. Here should be a bright fringe, you know it. Wave coming from here to here and wave coming from here to here, travel equal distances. They don't have any path reference. They must meet here. Okay, that is over. Now what else? Now let us select a point, and you know that this is D. We will transfer it later. Okay, this is D. Let us select a point on the screen, right? Point P, say, where the two waves meet. I don't know how do they meet. They may be meeting with crest on crest. They may be meeting with crest on trough. Don't know. That condition we will put it later. Let us select a point P on the screen where the two waves go and meet. This is joined here. This is joined here. And an arrow mark. Right? S1P is the distance traveled by the wave traveling from S1, first source. S2P is the distance traveled by the wave traveling from S2 up to P, second source. And shall I name this as D by 2? And this is D by 2. Just for my reference. Now, I want to get the equation for path difference. What is this path difference? Shall I write path difference as S2P minus S1P? This length minus this length is the extra distance traveled by S2, because from somewhere here this will also travel the same distance as this one, but this will travel extra. So S2P minus S1P is the path difference. Now if this path difference S2P minus S1P is equal to 1 lambda, this is the first bright fringe. Do you agree? Because this is needed now. Because I can't keep on explaining what is path reference now. That's why I have taken 2 to 3 periods just to explain what is path reference and phase difference. If the path reference of this one and this one is 1 lambda, this is the first bright fringe, other than the central bright fringe. Here is the bright place, and somewhere here will get dark and again a bright. And if this path reference is half lambda, this will be a bright dark fringe. So we will keep this open. Point P, we don't conclude that it is always bright and always dark. We will keep it open. This may be a dark, that may be a bright one. And when do you say that it is bright? We will have the condition L lambda, path difference is L lambda. When do you say that this point is dark? N plus half lambda, 1.5 lambda, 2.5 lambda, 5 lambda by 2, 3 lambda by 2, lambda by 2. For all those path references, this is dark fringe. So we will keep it as it is. Let us not give a name for this one, that permanently it is bright, permanently it is dark. We don't know. This is a generalized point P. Now we want to get this one. We will have to go to mathematics now. If you want to get what is S2P minus S1P, we will apply Pythagoras Theorem. What is S2P square? S2P square, S2P whole square is equal to D square plus, and let this point be at a height x from the central fringe. On the screen, this is the screen, I have selected a point which is at a height x from the central bright fringe. So what I can write, S2P square is equal to D by 2 plus x whole square, right? And this is D square. D square plus x plus D by 2 whole square. Am I right? D square plus x plus D by 2. The whole distance is D. D by 2 plus x whole square. Okay. What is S1P square? S1P square. Because I want this one. S1P square is equal to, this distance square is equal to D square, distance between the sources and the screen, capital D square. This one, what is this one? X, out of whole x, remove this half D. Then you will get this one. Plus x minus D by 2 whole square. Do you agree? Hope you have followed, right? This S1P whole square is equal to D square, capital D, and this height. This height is out of x, remove a D by 2. Then this will remain. x minus d by 2 whole square. Now expand this one, mathematics, purely mathematics now. S2p square is equal to a square plus a square plus b square plus 2ab. Correct? A square plus p square plus 2ab. What is S1p square? Hope you can see this, right? You can see this, whatever is written here. S1p square is equal to, shall I write it a little below? S1p square is equal to, or shall I write it here? I have a risk that it cannot be seen. S1p square. So I will divide this. Yes. Is equal to, what is S1p square? D square plus a square plus b square minus 2ab minus 2xd by 2. Okay? Now I want this one, right? So I will subtract the two. S2p square minus S1p square. S2p square minus S1p square. Now without writing completely, shall I do it here only? S2p square minus S1p square. S2p squared here, d square plus x square plus d square by 4. D square plus x square plus d square by 4. They cancel each other. xd minus of minus xd, 2xd. Everything else will get cancelled, correct? So I have to rotate once, otherwise the cable gets turned off. Yeah. So d square minus d square, x square minus x square, d square by 4 minus d square by 4. xd minus of minus xd, 2xd. Now shall I write this as a plus b into a minus b? S2p minus S1p, S2p plus S1p is equal to 2xd. Okay? So you know what are you doing, right? Where did we reach? What is your aim now? We are going to find out the path difference between the two waves while reaching at point P. We don't know what point P is, whether it is a bright point or whether it is a dark point. We don't know. But we want to know what it is. And by applying the rules that we have already. And okay, now the thing is, here S2P minus S1P, this is what is required. This is not required. But you can't neglect it. Now, all these things are here. You won't agree in the beginning with me, but finally you will have to agree. All these things are happening in terms of wavelength of light. Imagine what is the wavelength of a light. Angstroms, nanometer, 10 to the power minus 9. I just remember two persons putting their footsteps and going like this. Their footsteps will be 1 feet and 1.5 feet or 3/4 of a feet. What about the footstep of a light? If you take light as a small baby, light is having its footsteps in nanometers, and this is in nanometers, this is in nanometers. And when this distance is covered, every step is nanometer. How many nanometers will be required to cover this? So many nanometers. It's a small step. So that difference is very, very important now. Now you take here, this D is very large compared to this D. Right? This D is very small because the waves have to start from a very close point, otherwise they will interfere at very large angles. That is not proper for interference. They must go very parallel to each other, almost. So small d should be very small compared to capital D. So D is much, much smaller than capital D. In such a case, now suppose you have two sources of light and which are very close, and when you have a screen very, very far away, what about this distance and this distance? Suppose this is 100 centimeter and this is 100.1 centimeter. Only that much difference, because you are moving to a point which is very close to the central fringe. Say this is the central fringe. You are just moving above. This is 100 centimeter, this is 100.1. Only a very small difference between the two. Now, when you add them, when you add these two distances, S2P plus S1P. But in this diagram you don't feel that they are very close and this distance is very close to the central fringe and this distance is very small and this is very large. You have to imagine it. I can't draw a diagram of this one very close to each other and this is far away, because that gives the diagram very horrible. That makes the diagram very horrible and you can't identify all these things. You will lose mark. So if the sources are very close and if this is the central bright fringe and if this is taken here, then this one and this one are almost equal, then they are also equal to capital D, right? It is also equal to capital D. Or I will take some numerical example. Say this is the screen, this is the vertical distance, and say this distance and this distance, say this is 100 and this is 100. Now I will take a point here which is very close to this one. Say this is 100.1 and this is 100.1 and this is 100.2. This distance, this is 0.1 and this is 2. Why? Because the lower one has to travel more distance. This is 100.2, this one, and this is 100.1. Now when you add these two, what you will get? 200.4. Right? You will get is it almost equal to 2 into 100, 2 times this, because 0.4 can be neglected. So when you take a point just above the central bright fringe, if the two waves are traveling, when you add the difference in the distances between them, even though they have difference in the distance between them, when you add them, you will get almost equal to the double the distance between the sources and the screen. But when you subtract it, you subtract them, 100.2 minus 100.1, it is 0.1. Right? This is very small. But this can be taken as almost equal to double D. Right? So, can I write S2P plus S1P, S2P plus S1P almost equal to double D? Just see here, this is the actual situation. So, write S2P, S2, S1, S2P, S1P almost same as these two, because this distance is very small. This D, this D, this D, because this is 100, this is 100, this is 100.2, this is 100.1. Even if you add it, you will be very close to 200. You are not far away. So shall I write this as 2D? That is what I am trying to appeal to you. What about this one? Now sir, you have taken this as almost D and this as almost D. D plus D, 2D. What about here? D minus D, 0? No, it is not that one. That difference is important, because 100.2 minus 100.1 is 0.1. It is not 0. So this is taken as it is. Now why I am struggling so much to explain this is, at the end you will ask me, sir, when the sources are very close and the screen is far away, right? These distances are almost, all these distances are D, 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 everything is D. Even though this is little bit more, even though this is little bit more than D, it is not much more than D, and it is almost D. Then this D plus D is 2D. Then why don't you take D minus D equal to 0? That's not possible. You can't take it as 0, because that difference is so important. But when you add it, that difference is not so important. Why? You won't agree with with me now. Because you see 100.1 and 100.2, when you subtract them, what is remaining? 0.1, right? That is very important. That much itself is remaining. But when you add them, 200.4. Compared to 200, can't you neglect 0.4? But when you subtract it, remaining itself is 0.1. How can you neglect it? You will never. Sir, shall we write it as 0? No, not possible. If you write it as 0, everything will be 0. It has no meaning at all, because the wavelength of light is very small. So when you subtract the two things, you get the wavelength of light range. You can't neglect it. But when you add it, it is a difficult one. For example, if you go to a shop and purchase something in the shop, suppose it is some 1,000 rupees. You have purchased different items of 1,000 rupees. Now you ask the shopkeeper, give me a discount of 50 rupees, right? He will give you, or he may give you 20 rupees discount or 50 rupees discount. Suppose you go to that shop another time, once more, and if you purchase an item of 50 rupees, Now if you ask a discount of 50 rupees, will he give? No, isn't it? If you purchase 50 rupees itself, how can you ask 50 rupees discount? When you purchase 1000 rupees, out of 1000, 50 rupees discount is not a very dangerous one. You can ask him and he may give. But when you purchase 50 rupees, how can you ask a discount of 50 rupees out of 50 rupees purchase? Not possible. He may give you 5 rupees or 1 rupee. Similarly here, when you add it, it's a larger number, 200.4. Neglect 0.4, no problem. S2p plus S1p is almost 2d. But when you subtract it, you can't write it as 0. It is that difference. And moreover, we are struggling to get the difference itself. S2p minus S1p itself is what is needed for us. That is the path difference. Remember, when two waves, light waves with small steps are moving like this, their step difference is very important, even though it is very small. So, shall I continue? And see, still if you have a doubt that, sir, this is d plus d almost 2d, this is d minus d 0, why not so? You just put a WhatsApp message and argue with me that it should be 0. I will have my own argument and we will spend time later, not here. Okay? So this is what is needed for us. So what you will get? S2p minus S1p is the path difference, 2xd by d or 2d, and this is cancelled. So path difference between the waves is xd by d. Derivation is not over. We are still, we have not yet found out the fringe width. What is the distance between two successive bright fringes, or what is the distance between two successive dark fringes? That is what we are going to do now. It is a very famous derivation. As examination is concerned, theory exam is concerned, entrance exam or knowledge wise, everywhere it is important. What is path difference now? This one. Now, what is x now? Okay. There we have got path difference itself. Now, let us assume that this is the bright fringe. Point P is bright fringe. Okay? It is a bright fringe. Let us assume that P is a bright fringe. If it is the nth bright fringe, maybe first, second, third, fourth, anything. If it is a first bright fringe, what is the condition? It is 1 lambda. If it is the second bright fringe, 2 lambda. If it is the third bright fringe, 3 lambda. You are going on adding 1, 1, 1. If it is the nth bright fringe, n lambda. Suppose it is the next bright fringe, n plus 1 lambda. Am I right? If it is 9th one, 9 lambda, path difference. If it is the 10th one, 9 plus 1, 10 lambda. Suppose it is nth bright fringe, then the path difference is, if this is nth bright fringe, say x1 I will write. Or I will turn this formula, path difference into d divided by d is equal to x. I'll write it like this, okay? This path difference into d by d into d by small d is equal to x. If this is the nth bright fringe, then what is the distance of the nth bright fringe? For example, 7th bright fringe. If this point is the 7th bright fringe, what is the distance of the 7th bright fringe from the central maximum, the maximum bright fringe at the center, which is 100% sure that this is a bright fringe. If this is the point of the 7th bright fringe, what is its distance? xn. Distance of the nth bright fringe is equal to, what you have to put here? n lambda, path difference condition, d by d, equation 1. No sir. Here you will get another bright fringe above that, and its distance is different, x2. So if you still, if you move above little bit, you will get another bright fringe. Which is that number? It is the 8th bright fringe. So what is the distance of n plus 1th bright fringe, which lies just above this, right? This is xn, this is xn plus 1. It is n plus 1 lambda d by d. This is the next bright fringe. Now what do you mean by fringe width? It is the distance between two successive bright fringes. Are they not the successive bright fringes, 7th and 8th, nth and n plus 1th? Their distances are xn and xn plus 1. So what is fringe width beta? xn plus 1 minus xn. From here to here distance minus here to here. this is the bright fringe width, distance between two successive 7th and 8th bright fringe, that is beta. So shall we subtract them? That is equal to, so here lambda d by d, here lambda d by d. Both places you have lambda d by d. Lambda d by d common. What you will have here? N plus 1 minus n. Have you followed this? Can you see this first? You can't see this. I think you can't see this. Okay, shall I write it here? I will bring it here. Okay, this is the safe place. Okay, now x equal to path difference, x equal to path difference into capital D by small d. Okay, let us assume that this is the 7th bright fringe or nth bright fringe. What is the condition for nth bright fringe path difference? X is equal to n lambda capital D by d. This should be n lambda. Another person says, sir, just above that I have one more bright fringe, which is the next one, 8th one, or n plus 1th fringe. So this is xn. What is xn plus 1? Just above this, xn plus 1 is n plus 1, 7th to 8th, lambda d by d. So what is the distance between nth and n plus 1th bright fringes? The distance between them is xn plus 1 minus xn. For example, the 7th bright fringe is at a distance of say 10 millimeter, and the 8th bright fringe is at a distance of 12 millimeter. Distance between them is 12 minus 10, that is 2 millimeter. That is the fringe width. So distance between two successive bright fringes, n plus n and n plus 1 and n, that is this minus this. And here you have a lambda d by d, here you have lambda d by d. Make it common. Remaining thing you subtract, n plus 1 minus n, that is lambda d by d. So this is called beta, the distance between two successive bright fringes, that is lambda d by d. This is the answer. Okay, now where is this x? It is here. So shall I rub this? Yes. This is the distance between two successive bright fringes. Or now what is the distance between two successive dark fringes, sir? So can you see this one, right? Beta is equal to lambda d by d. Beta is equal to lambda d by d. I don't know. I must guess whether you can see it or not, because there are nobody today behind the camera. I myself is shooting this one. I don't know what is happening in the camera. I am just guessing that everything is getting recorded, and I am doing this. Okay. Now, sir, what should be the distance between two successive dark fringes? Whether dark fringes are equally spaced, they should be, isn't it? Whatever be the first bright fringe, then you will get dark fringe in between, bright and bright, in between you will get dark, again you will get dark here. They must be equally spaced. Let us try to get the formula for distance between two dark fringes. Now, where is that? X equal to path difference into capital D by D. Sir, let this be a nth dark fringe. What is the condition, sir? If it is nth dark fringe, condition is n plus half lambda. You know that. Because when n is 0, lambda by 2, half lambda. When n is 1, 3 lambda by 2, 1.5 lambda. You know that difference. And when n is equal to 2, 2.5 lambda, 5 by 2 lambda. So like that. N plus half lambda, first path reference, into d by d. Okay, that is one thing. Suppose you have one more dark fringe above this, that is the next one. That is n plus 1 is n plus 1 plus half, right? Next one. That is lambda d by d. What is this? n plus 1th bright fringe. n plus 1th bright fringe. Distance of the n plus 1th, next dark fringe, next dark fringe is n plus 1 plus half. That is n plus 3 by 2. Am I right? 1.5. This one, lambda d by d, correct? This is the next dark fringe, this is the previous dark fringe. Subtract them. What is beta? Beta is the difference between these two. So shall I write lambda d by d first, and remaining, what is this? N, here you have, n plus 3 by 2 n plus 3 by 2, where is this? N plus 3 by 2 minus n minus half. What you will get? N plus 3 by 2 minus n minus half. Lambda d by d is common. What you will remain with? N gets cancelled. What is 3 by 2 minus 1 by 2? 2 common. 3 minus 1 is 2. 2 by 2. That beta is equal to lambda d by d. You get the same answer as this one. Right? Did you get this? This is n plus half for first dark fringe. For first dark fringe, half lambda difference. 0 if you put. But we are generalizing it. N plus half. Next dark fringe, you have to put one more, n plus 1 plus half, that is n plus 3 by 2. Subtract these two, lambda d by d, you take it common. Then remaining subtraction, n plus 3 by 2 minus n plus half, minus n minus half. 3 by 2 minus half is 2 by 2, 1, lambda d by d. So this is the expression for the distance between two successive bright fringes or two successive dark fringes. Very, very important formula, and we are going to analyze it in different ways. But for the time being, derivation is enough. But when you come to the next class, you must be ready with this derivation. You should be thorough with this derivation. Very important derivation. 100% either derivation or problem from this in the final exam. No doubt. So study this, be ready with this answer. We will meet in the next class, right, with the analysis of this and few more problems. Thank you for watching. Thank you. Thank you.